Good morning, everyone. Welcome to our webinar series. I'm Erin Elliott. I'm an optical engineer here at Zemax. And before I joined Zemax, I spent over a decade working on the James Webb Space Telescope, or JWST. So we thought it would be fun to have a webinar on the telescope. In this first webinar, we'll talk about the mission and do just a little bit of modeling work at the end. Hopefully, in future webinars, we'll take a look at the telescope's design and how to model the segmented primary mirror. So a lot of people ask me why we should build space telescopes. So I've developed kind of a standard plug for why we do astronomy. This plot represents the evolution of the universe. We start with the Big Bang, 13.7 billion years ago, and then we pass through the Dark Ages, when nothing in the universe was emitting light. Then you get to the first stars about 400 million years ago, when the first light-emitting objects appeared in the universe. Then you go forward 13.7 billion years to the present day, when we live a universe that's expanding and accelerating that expansion, propelled by dark energy. We don't know exactly what dark energy is yet. We only know it's there by its effect on the universe. So when people ask me why astronomy is important, I say it's trying to answer the biggest questions in life right now. How did you get from the Big Bang, 13.7 billion years ago, to the first atoms and all the way up to DNA and to people? There are questions that are related to that, of course. How did life begin? Is life rare or common? There are a lot of planet-finding missions out there working on that right now. And another interesting question is, what is the ultimate fate of the universe? Even though we won't be around to see that, it's still a pretty interesting question to ask. In order to answer the questions, we need to understand all the steps along the way in the evolution of the universe, starting with the Big Bang. How did the first stars form? How did galaxies and planets develop? These are the questions that astronomy is tackling right now. So JWST, of course, by itself won't be able to answer all of those questions, but it will definitely take us closer to the answers. JWST is an infrared space telescope that's scheduled to launch in 2018. It's much larger than anything we've flown before. It's a general purpose observatory like the Hubble Space Telescope, so groups will submit proposals and compete for time on the telescope so that the projects with the most scientific merit are prioritized. It will collect 6 times as much light as the Hubble Space Telescope because it's a much larger telescope, and it will see objects in higher resolution. That basically means that it'll see older, colder things in the universe. In particular, it will be able to see all the way back to the first light-emitting objects that formed in the universe, right at the end of the Dark Ages. The telescope is big enough to collect those very faint, very old signals. Many of you are probably familiar with the Hubble Space Telescope. It's a general-purpose observatory, and it really revolutionized our understanding of the universe. Half the things that it has done were unknown when the telescope itself was built and launched. But Hubble is a much smaller telescope than JWST. So here's a comparison of an image from the Hubble Space Telescope to one that we'll get from JWST. You can see that the JWST image shows more objects in the picture, and it also shows more detail, which you can see in the spiral galaxy at the center. So really, there are 2 reasons to build larger space telescopes. You get more light gathering power or sensitivity, and you also get more detail or resolution. And just incidentally, this is an actual Hubble image from the Wide Field Camera 3 from the infrared channel. This is a simulation of what we'll see with JWST using its NIRCam camera. So the lower one is a simulation. Okay, so let's get into the nuts and bolts of the telescope a little bit. So this is an artist's rendition of the James Webb Space Telescope. This is the primary mirror. It has 18 hexagonal segments. The secondary mirror is out here on struts. Then back behind the primary is a tertiary mirror and a flat fold mirror in the front of this assembly. The cameras are mounted here in the ISOM assembly along the back. And down here at the bottom is a sun shield, a multi-layer sun shield that protects the telescope from the sun and earth radiation. And the spacecraft at the bottom does all of the flying, the communications, and the electronics. This is a schematic of the 18 mirror segments. They're 59 inches point to point. The total enclosed diameter is 6.6 meters. Each mirror segment is polished to be less than 1/10 of a micron, and the segments are coated with gold. For comparison, here is Hubble's primary mirror, which is 2.4 meters in diameter. There are 5 cameras on board JWST back in the Science Instrument Module located behind the primary mirror. Each camera in this schematic in the upper right, each camera occupies a different space in the telescope's field of view. So the full telescope has a field of view of about 9 by 18 arc minutes. And each camera occupies a different space in that field of view. These cameras don't usually run simultaneously. They run separately. You point at the object that you want to observe. So I already mentioned that JWST is an infrared mission. It'll see a lot further into the infrared than Hubble did. JWST observes in the visible at 0.6 microns and goes all the way out to 28 microns. Hubble, for comparison, observed from about 0.12 microns out to 2.4 microns. Many of these long infrared observations can't be done from the surface of the Earth. There's a couple problems on the Earth. The atmosphere, of course, causes turbulence, which adds blur to any images collected by Earth-based telescopes. But also, many of these long infrared wavelengths are absorbed by the atmosphere. This is a plot on the lower right of atmospheric absorption versus wavelength. And when you get out to the infrared, you see that we're well outside the optical window where human vision occurs. And we're getting pretty significant absorption at many of these infrared wavelengths. Moving into space solves both of those problems, atmospheric turbulence and atmospheric absorption. And it solves another problem too. Because JWST observes in the IR, everything warm that emits in the IR could swamp the detectors. The detectors are really sensitive. So it has to be protected from the sun's emissions. It has to be protected from the Earth's emissions because everything on the Earth is relatively warm, thanks to the radiation from the sun. And the parts of the telescope itself have to stay cool so that the telescope structure doesn't emit in the infrared. So the telescope has to be cooled to roughly 40 Kelvin or negative 390 degrees Fahrenheit. Which the sun shield is designed to do. On this plot, you can see that the sun's peak emittance is somewhere around 0.6 microns, and a filament tends to run a bit hotter. The Earth radiation tends to peak at 10 microns, which is still well inside the observing wavelengths for JWST. So everything on the Earth could potentially swamp the JWST detectors. So if we get the telescope down to 40 Kelvin, you can see that the beginning of the emission curve out here at 30 microns for those parts. So 40 Kelvin is the magic number so that the telescope parts don't swamp the infrared detectors. So where will JWST fly? The choice of orbit affects the temperature of the telescope as well. So part of the way that we control temperature is by choosing an orbit that's far away from the Earth and Sun. JWST will fly out behind the Earth, basically, about 1 million miles away from the Earth. It orbits the Sun in a semi-stable point called L2. As the Earth goes around the Sun, the telescope stays on this line that joins the Sun and the Earth. It's a semi-stable orbit because if the telescope were to fall behind, you could imagine that the gravitational field of the Earth would tug it forward. And if the telescope were to somehow get ahead, the gravity of the Earth would tug it backwards. So that's the semi-stable aspect of the orbit. The sun shield of the telescope faces the sun and the Earth in order to block that radiation from reaching the telescope parts. It also prevents the radiation from heating the telescope structure to unacceptable temperatures, as well as just blocking the direct radiation from the sun and the Earth. This is an artist's rendition of what it would look like if you were out at L2 looking back toward the sun. I think this is an artist's rendition because the Earth and the Moon would probably actually be much darker. I think the intensity of the sun in this image has been damped down. Incidentally, the exact orbit about L2 is chosen so that JWST stays out of the Earth's shadow. That's so that the telescope doesn't experience temperature swings as the telescope travels in and out of the shadow. Even if you could find a very small, stable orbit that stayed behind the shadow, the temperature variation is still unacceptably large because the shadow of the Earth isn't equally dark everywhere. Okay, so how do we get there, way out to L2? JWST will launch on an Ariane 5 rocket. There's a photograph here of an Ariane 5 launch. It launches from French Guiana, which is in South America, near the equator. The Earth's rotation gives the rocket an additional helpful push during launch. Because JWST is so big, it needs to fold up to fit in the rocket fairing. That's shown over here on the left. The primary mirror has two wings that fold back with 3 segments each on them. And the sun shield folds up into 2 pallets at the front and the back of the telescope. We, of course, have to keep the weight of the telescope as low as possible, below 14,000 pounds. If the payload weighs more than that, the rocket will move too slowly after it leaves the Earth, and it will take us longer to get to L2. As planned, it will take several months of travel time to reach L2. If the telescope is much lighter, it could travel faster, but that's not necessarily a good thing. If we're going faster than planned, we need to brake harder when we get out to L2, which wastes more of our precious onboard fuel. As the telescope travels out to L2, it unfolds itself. Here's a video of the deployment. This video is taken from an excellent website at jwst.nasa.gov, and of course you can go there to find out more of the details of this mission. So let's watch this deployment video. So that is the solar panel deploying. It unfolds. Now the communication antenna is dropping down and facing the Earth for communication. Then the first pallet of the sun shield unfolds. And the second one, and down here you can see the star trackers. We'll talk about pointing the telescope a little bit more when this video is finished. Now the telescope boom deploys. This takes the telescope further away from the sun shield and helps cool the parts further. The sun shield unfolds. And deploys. And then after the deployment of the sun shield, the multi-layer stack unfolds. Now the secondary mirror deploys, the spiders unfold, and the 2 wings of the primary mirror come forward. And at this point, each segment in the primary mirror is not yet aligned. There's a process for doing that we're going to talk about in a minute. But that finishes the major steps of deployment. And here we're going to see the star trackers going by again. So Pointing the telescope is pretty interesting. You can get really coarse pointing from the thrusters, but you want to use the thrusters on the spacecraft as little as possible, because all the fuel for the telescope's lifetime has to be carried on board at launch. In fact, the lifetime of the telescope is limited by the amount of fuel that we use. The less we can use, the better, the longer the telescope lives. For somewhat finer pointing, we rely on the star trackers, which you can just glimpse at the bottom of the image here. So the star trackers lock onto a pattern of stars. You can see that there's 3 star trackers there. And then they run in an automated loop with the spacecraft's gyroscopes to keep the telescope pointing stably. For fine pointing, we rely on the fine guidance system, which you saw in the layout of the telescope's field of view. That system runs in a closed loop with the fine steering mirror, which is a flat mirror located out here in the front of the assembly. So for very fine pointing, the fine guidance system controls the fine steering mirror. After the primary mirror is deployed, all the 18 mirrors are pointing in a slightly different direction. If you were to look at one star, you would get 18 out-of-focus images like this, instead of just a single image. The mirrors have to be perfectly aligned to work as one mirror. So to do that, each mirror segment has actuators that move them around. The alignment process is referred to as wavefront sensing and control. And we used Zemax software extensively to help model the motions of the mirrors and the wavefront sensing and control process for the telescope. Incidentally, in the picture of the segment, you can see that the back of the mirror isn't solid. It's been extremely lightweighted. That's one of the ways that we save mass. Everything that can be lightweighted is lightweighted. Okay, so the wavefront sensing control process is fairly complicated. It's 100% image-based. So the alignment of the segments is done purely with images that we collect in the NIRCam instrument. NIRCam is also used for scientific observations when we're not busy using it for alignment activities. So let's go through a few of these steps just so you can get a sense of how this is done. First, we sweep around to get a sense of the telescope's bore site. Then we find the best position that we can for the secondary mirror, given that the segments are still a little bit out of focus at this and mispointed at this stage. We go through a segment identification process where you tweak each segment in order to figure out which segment controls which spot in the image. If there are any segments missing, we go through a segment search routine. Then the segment images are all arranged in a grid, and each one is corrected as much as possible during a global alignment. We then stack the images up, and at this point we start getting our first look at the pupil images of the primary. So now we can actually look at the primary mirror segments, or their image on the NIRCam instrument. Then we move on to coarse phasing, which is used to correct piston errors between the segments. Basically, in coarse phasing, we use spectra to find the relative piston between the segments and correct it. Finally, we get our first wavefront maps and our first PSF measurements, and we use those to fine-tune the imaging. And then last, we carry out a multi-field process to check that the alignment is good over the full field of view of the telescope. We used Zemax, controlled by IDL, to model and test this whole alignment process. We also had a 7-scale testbed telescope where we could test the alignment process in real hardware. That was built by the excellent team at Ball Aerospace. And we created Zemax models of the testbed so that we could simulate any changes to the testbed before we moved to the real hardware. This is a photograph of the 7-scale testbed that was built to test out this alignment process at Ball Aerospace. And we had a Zemax model of the testbed. It's a double pass system, and a schematic of it is shown here. All the segments move in 6 degrees of freedom, about a coordinate system that's tangent to the back of each segment. So we had a Zemax model of the testbed, a Zemax model of the flight telescope, and the testbed itself. All 3 of those could be controlled in IDL, and we could run trials on the testbed in the model before we carried them out in the hardware, and we could also compare the results to what was happening to the flight model. All of this was done to verify that the wavefront sensing and control process would work. Okay, that's probably more than you wanted to know about alignment. So let's take a step back a little bit and look at the basic design of the telescope. JWST is a 3-mirror anastigmat, a TMA. If the mirrors are selected carefully, this design has enough degrees of freedom to correct for spherical aberration, coma, and astigmatism. The prescription is in an optical engineering paper by Paul Lightsey, which I've cited here so that you can look it up. And you might want to grab a screenshot of these numbers because we're going to next start on a little model of the JWST telescope. If you have Optics Studio open, you can open a new file, File New, and start working with that. And hopefully you can follow along as we build this telescope model. So first, I'm going to add a few surfaces using the insert key on my keyboard. And then I'm going to label them so I know what they are. So this surface 1, I'm just going to call plot begin. It's a place to launch the rays in the layout plot. And then we need a primary mirror, which you can see is also the stop surface, as it is for most telescopes. Here's the secondary mirror, tertiary mirror. Then we need the fine steering mirror, which is just a fold flat, and the image plane. So the image plane in this case is where the pickoff mirrors would be positioned in order to send light to each of the cameras that is on board. Okay, so I'm going to make the thickness of the plot begin surface 10,000. My units are in millimeters. And let's start by entering the radii of curvature of the mirrors. The primary mirror is concave, and the curvature is 15,879.7. The secondary mirror is convex. The system is changing to propagate along the negative z-axis, so the correct sign of this radius is also negative, negative 1778.9. And the tertiary is concave as well, with a radius of curvature of 3016.2. The fine steering mirror will leave the radius at infinity because that's a flat mirror. Now, the distances between them, the distance from the primary to the secondary is 7169. The distance from the secondary to the tertiary, we have to calculate. We have to add the 2 numbers listed in the table together to get 7965.3. And the distance from the tertiary to the fine steering mirror is negative 1844.1. And then finally, the distance from the fine steering mirror to the image plane is 3027.434487. That is probably more decimals than is strictly required. So that gives us our thicknesses. And all of these are reflective, so I'm going to put in a mirror material on each line. Okay, so that's our basic setup. Let's go add a couple more things. first of all, let's add an aperture diameter over here in the System Explorer. We want the entrance pupil diameter to be 6.6 meters. It's actually 6605.2. And the wavelength doesn't matter too much because we've got a reflective system here, but I'm going to change the wavelength to 1 micron. So that gives me an aperture of 6605.2 and a wavelength of 1 micron. And finally, let's add some field points. So we said that the field of view of the full telescope is about 9 arc minutes in the y direction and about 18 arc minutes in the x direction. So it's a rectangular field, so I'm going to choose here rectangular normalization, and we'll get to why that's important later. And I'm going to create 9 field points. I'm going to choose field points at plus or minus y, plus or minus x, and then at the corners of the field for this telescope. So if I do the math, I'm entering these in degrees instead of arc minutes. So in the x direction, I enter negative 0.152 degrees and positive 0.152 degrees. And in the y directions, I'm going to enter 0.076 degrees, positive and negative. And now I want to do the field corners. So okay, so these are the field angles I have, plus or minus x, the plus or minus y, and the 4 field corners. Okay, so that's our fields of view. So we have an aperture, we have fields of view, we have wavelengths, and we have our mirrors. Let's take a look at the layout plot and see if we got this right. So I'm going to the Analyze tab and I'm going to choose the 3D viewer. And I have my system set up so that the settings appear first. And I've selected Suppress Frame. And I'm going to choose just the first field angle, which we left at 0, 0. That's the on-axis field angle. And I'm going to start with surface 1 and end with surface 6, which is the image plane. Okay, so what's going on here is that we have not yet entered the conic constants for the mirrors. So right now, all of these mirrors are spherical. Almost all reflective telescopes use conics instead of spheres. So let's go ahead and enter the conic constants. The primary conic is 0.9967. You can see it's almost a parabola, but not quite. That's because parabolas do have a perfect focal point on axis, but off axis they acquire coma really rapidly. So most telescopes do not use a perfect parabola, but use something that behaves a little better at the off-axis field points. The conic for the secondary is negative 1.6598, which makes it hyperbolic. And the tertiary's conic is 0.6595. Okay, so we have those numbers in place. Let's look at the layout plot again. That looks a little better. You can see that there's a focus here after the secondary mirror. So let's do a couple things to clean up this plot. I've chosen surface 4 as my last mirror shown for now as we troubleshoot. And I'm going to also select this Hide Lens Edges flag here. If I do that, it looks more like a clean 2D layout plot. And then let's go, I'm going to go back and go all the way to the image plane now to check that this on-axis field point looks right. Okay, so that looks good. You can see that the rays come in here, come to the secondary, here they come to a focus, they get to the tertiary, they're folded back to the fine steering mirror, and then they get to the image plane. Now here we kind of have a problem because the rays are magically going through the fine steering mirror on the first pass, and they're also magically passing through the tertiary to get to the image plane. So in JWST, that's handled with a bit of a field bias, meaning that the on-axis field point of the telescope is actually a little bit off-axis. So to model that here, I'm going to insert an extra line, and I'm going to choose the coordinate break surface type. And I'm going to call this a field bias. This will be a constant offset in angle that the whole telescope experiences. And I actually don't remember the exact value for this field bias, but I think it's about 0.16 degrees. So on tilt about x, I'll put in 0.16 degrees. This tilts the whole telescope with respect to the incoming field angles. And if I update that, you'll see that that makes a little bit of room for the fine steering mirror. So now these rays are coming in at a slight angle, hitting the secondary, coming to a focus as before, but now the rays hit an off-axis piece of the tertiary, and then they come back to hit this fine steering mirror, which is flat, and they go to the image plane out here. Okay, so that's the basic telescope design. Let's go back into the layout plot and turn on all the field angles just to see where those fall. So you can see that our image plane is down here. Okay, and let's do a couple more things. Let's look at the spot diagrams. If I go up here under Analyze Rays and Spots, and I choose the spot diagrams, I need to do all field angles at one wavelength. Okay, you can see that this telescope doesn't look like it's in focus. These are uniform spots that look like defocus. You can see that they're quite bad out at the corners of the field. Let's also look at the spot diagram, footprint diagram for the image plane. That's under Analyze Rays and Spots, Footprint Diagram. And I want to look at the image plane for that and all wavelengths and field angles. I'm not going to use symbols. And I'm not going to delete any vignetted rays. Okay, so you can see if I zoom in here, these are the field points that I've defined on the image plane. They're in a rectangular configuration. And it's a little bit difficult to see on this plot, but you can see that the spots are getting larger as we move down in the y direction. So the footprint diagram shows us where each of these spots physically falls on the image plane, and the spot diagram shows us the quality of the spots, which right now is not that great. So let's fix that. The problem here actually is that the image plane is tilted, should be tilted and off center from where we currently have it. And you'll see that there's an additional problem as well with field curvature. So in order to move that image plane, I'm going to add another surface here, another coordinate break surface that will let me move the image plane around. I'll take this thickness off the fine steering mirror. I'll take this thickness off the fine steering mirror and put it on the coordinate break instead. I just used Control-C and Control-V to do that. And then here I'm going to do some chief ray solve. So what I want is, after the fine steering mirror, I want the coordinate system to follow the chief ray to the image plane. I'm going to switch back to just one field point so you can see more clearly which ray I want it to follow. So I want the coordinate system to follow this gut ray to here. And so I can see that my image plane has to decenter a bit in y, and then it also needs to tilt about x in order to be perpendicular to that gut ray. So up here under y decenter, I'm going to do a chief ray solve for field number 1, which is our on-axis field point. That should return the amount of decenter that I need. And then under tilt about x, I'm going to do another chief ray solve on field 1, the on-axis field point, and that should give us the tilt on the image plane that we need. So let's do that. And I'll go here to the layout plot to see what that looks like. That's better. This now, it looks centered and perpendicular to the gut ray. But now there's one more problem that we need to solve, which is if I update these spot diagrams, you'll see that they make a little more sense now. The 4 corners of the field are balanced. And things at the on-axis field point look pretty in focus, but these spots are still not very high quality. They're still quite a bit out of focus. So if you have an in-focus spot at the center of the field and out-of-focus spots elsewhere at the corners of the field, that's a clear indication that what you've got is field curvature. So this image plane actually wants to be curved. And that's fine because remember, we aren't putting detectors here. What we're putting here is pick-off mirrors that go to the various instruments. So we can adjust for this defocus later on in the instrument, which is fine. So for our telescope model here, let's do a couple things. Let's allow the image plane to be curved. So we'll allow it to have a radius of curvature that matches the field curvature of the telescope. And we'll also set the thickness to the image plane, the distance to the image plane, to be a variable. You can do that by clicking here on this box and choosing variable instead of fixed. We do the same on the radius of curvature for the image plane. Okay, and over here on optimize, we'll set up a merit function. We're just going to set up a simple merit function based on spot radius. Nothing fancy, and we'll hit OK. Okay, that populates a merit function for us. And we have 2 variables, the radius of curvature of the image plane and the distance to the image plane. So I'll save that file and optimize. And you can see that the merit function drops really rapidly. So let's go see what changes it made. It shifted the image plane just a little bit, and it gave us a 3-meter radius of curvature. So that's the field curvature that's coming from the telescope. If I update that, you can see this curvature appear. I can zoom in on that. You can see that there's now some curvature on the image plane. And if I go to the spot diagrams, I can see that they're greatly improved. Now I've got a mostly diffraction limited system over the full field of view. And you can see that there's just a little bit of higher order coma creeping in at the corners of the image plane. Okay, so this is the TMA design that is the basic, that the James Webb Space Telescope is built on. So we've done a basic TMA design now for JWST. In the future, we can add some things to this. Hopefully we'll do some webinars. We can add apertures to the mirrors, and we can add a secondary obscuration and some spiders. We can also add individual primary mirror segments, and we can make those move so that we can simulate the alignment process. And then also, hopefully in future webinars, we can look at some other interesting telescopes. Hubble is a really interesting telescope to look at. It has a very wide field of view. We could also take a look maybe at the Kepler design. Kepler is a planet hunting mission. And there's others we could look at too. So if there's anything you're particularly interested in learning about, do let us know. Thank you so much for your time. And I'll be online after this for a Q&A session.